turns out presenter mode somehow makes QuickTime pause whenever I switched from a slideshow back into the normal desktop, so I wasn't recording anything. But without presenter mode, I just tested it. It seems to work, but who knows what's going to happen. You can also blame your fellow classmates, because I posted some videos and I didn't understand why I was recording 50 minutes of class lecture when we had 115 minutes of class. And so it turns out it was because it was not recording times when I switched over. So yeah, that's the way it goes sometimes. So I guess a little, yeah, okay, so this is everything that we had last week. I won't talk about it, but you can see this nice jumble of handwritten notes. Beautiful code that we wrote. Look at us coding in assembly. All right, that's all good. Okay. So now we will continue. So now we're going to go fairly quickly through this remaining material and slides we have on the x86 stack, on function frames, and on calling conventions. Do you have any questions before we start? I guess we can also do something else. Do you guys want homework before spring break or after?
After. Before.
Does it affect the due date?
Yeah.
It'll have to be the same amount of time due.
After.
After. That's what I thought. Okay. Good. I have a hacking competition set up on Friday, so I'm a little slammed anyways, so I'm glad we're on the same page. All right, yeah, we're hosting, I think they just said there's 300 teams registered now, and so we're setting up the infrastructure to host everything on AWS in the cloud, and so we have to, but not only, so you have 300 teams, each team is running 10 custom services that we have written that have specific vulnerabilities, and so what you have to do is about every 5 or 10 minutes, you have to test every single service on everybody's team to see, is this service still up and functional, right? Because it's really easy not to be hacked. What do?
Shut down the service.
Shut it down, yeah, shut it down, right? Nobody has access to it, it's great, it's super secure, nobody can hack any of your flags, right? But then you should lose points because that's not fun, right? Because everybody just turns their services off. It's not a fun game. So we have scripts that are running and constantly monitoring everything. And so we're trying to, that's actually the key component right now. We're trying to scale to see how we can test all these services correctly. Because apparently 32 cores and 60 gigs of memory was not cutting it. So we need more. Yes. Questions?
Yeah, can we use reflector?
You can try. I don't think it'll do anything. Yeah, that's interesting. I don't know. We'll see. If it works, you should let us know because that's not intended. All right. Okay, so back to binaries. So we need to focus and we need to study and really understand at a very core technical level what exactly happens in an x86 binary and how exactly functions look. So we saw that applications on the stack, functions on the stack will create a function frame. And what information is stored in this function frame in addition to local variables?
Like the line of the function, or like the line to return to on the stack.
It's not a line. What is it exactly?
Memory
Whose memory location?
of the calling function.
The same VIP, so the caller's instruction pointer, right? So that's in the function frame, right? And how does that get onto the stack? What instruction puts that there? It's a call instruction, right? The call, so when the caller calls the callee, right? When it says call foo, that instruction pushes the next instruction pointer onto the stack. So that becomes the same VIP. So we have same VIP, we have local variables, what else? The arguments, the parameters to the function, which will be where?
On the stack. Below.
On the stack, where in relation to, say, VIP? Above. In what order, starting from the bottom up?
Right.
Left to right, starting from the bottom up. Yes. It's always tricky, but just gotta remember exactly how it looks. The leftmost parameter will be the one right above EIP. The second parameter will be right above that. The third parameter will be right above that. So if you're going to push them onto the stack, you go right to left. Push, push, push. Okay. What else? So we got that. We have EIP. We have parameters. We have local variables. Somebody over here. What else? What's the saved base pointer?
The base for that particular, I mean, where you can start looking at the parameters for the next function.
Right, but where did it come from? Yes.
B is B at the start of the call use function.
Yes, so when the call, well, what about the saved base pointer that's actually saved on the stack? Where did that come from? Whose base pointer is that? The caller, yes, exactly, right? So the caller gets called, and then it sets their base pointer to the current stack pointer, but before it can do that, it has to save whatever was in the ESD register, EVP, yes, EVP register. That's to save that on the stack. And where is that in relation to all the other variables we just talked about? You wanna go? Go.
The caller, like whatever.
In what order? Where is it in relation to all the other things we just talked about? We're specifically talking about like 5 things. Yes. Below EIP and above what? The local variables. Yeah. So remember we have arguments, and maybe we can see if this thing works. Okay. We're at 7 minutes. We're still recording. Hopefully. Yeah, it's ticking. That's good. Okay. So just like we drew here, so we can go back to our beautiful reference diagram. We have arguments, so we first have the arguments on the stack, then we have the saved EIP, then we have the saved base pointer, and then the local arguments. So this is exactly what the stack looks like for every function. So every function will have its own function frame. Cool. And we talked about we cannot use the stack pointer because the stack pointer constantly moves as the program executes. And so the base pointer will point to the start of the function's frame, although in x86 it's a little bit weird because it kind of points in the middle, right? So when it wants to access when it wants to access parameters, what offset is that from EVP? Positive, which in the direction we draw the stacks, which direction is that? Up. So parameters are going to be up, and local variables will be where?
Down.
Negative offsets, yes. And that's how you can always tell. Okay, now we're going to start an EVP. So we'll go very quickly through this example. We have a function main. It has 3 local variables, A, B, and C, different types. We set A equals A plus B, and then we return 0. So we can think that the compiler, we talked about this a little bit, right? At high level, we'll just decide on an offset of the base pointer for A, B, and C. And we talked about it's a local variable, so the offset will be negative from EVP. So it will say that A is at some offset from EVP, B is at some offset, C is at some offset. And so the pseudocode, if you think about it from a high-level pseudocode, is, hey, set the memory location at EVP plus A to be 10, set the memory address of EVP plus B to be negative 100, set the memory location of EVP plus C to be 10.45, and add them all together. And so when you compile this, right, there's no specific order that things have to be in to correlate between the C code and where they are stored in relation to EVP. When I did this, it just happened to be that A was at EVP minus hex C, B was at minus 8, C was at minus 4, and the code translates very similarly. So we have moved the stack pointer into the base pointer. So what's this doing?
Saving the base.
Setting the current function's base pointer. What are we missing here? What didn't I include here? Saving the old base pointer. So there better be a push EVP above here when we look at the real program. Then we subtract 16 from the stack pointer. We move, what's hex A in decimal? Move 10 into EVP minus C, which is doing what? Yeah, in the back.
It's assigning value of 10 to the variable A.
Right, so assigning 10 10 into the memory address that is associated with the variable A, exactly. Then we're moving hex 64 into EBP minus 8. Then we move this crazy hex value into EAX. What is this? A float? What kind of a float? If you wanted to decode this, how would you figure out how to interpret this? Well, the next one is just moving EAX into EBP minus 4. We haven't got to the add yet. Who's complement? Yeah.
Gonna be, no, I don't think so, but I would assume it's gonna be the decimal representation.
Say it again?
The decimal representation.
So what type of decimal representation? Yeah, IEEE floating point, yes. There's a specific specification you can look up to know exactly how to represent this floating point number. And so how do you know it's a float and not a double? Yeah, there's 32 bits here, right? A double is 64, I believe. Or is it bigger? I think it's 64. So why did the compiler do these two steps, right? Think about what it's doing. It's moving this hex representation of 10.45, the IEEE floating point representation of 10.45. It's moving that into EAX and then moving EAX into EBP minus 4. Why?
Is it to make sure to know the length of that particular one?
Make sure to know the length, but it's using EAX, so it'll use 32 bits. Huh? Yeah, who knows? Because the compiler decided it's faster for whatever reason. It's kind of a trick question, but it can get you to think about, you need to think about the semantics of what are happening, right? Not the actual instructions. You need to think at a high level, hey, this is just moving this value into EBP minus 4. The fact that it takes 2 instructions versus 1 instruction for the other 2, it's essentially the same thing. This compiler just decided to do it this way. Then we move EBP minus 8 into EAX. So what's the value that's going to be inside the EAX register at this point? 8? What was it? Decimal. What is it? 100? And then it'll add EAX to what's in EBP minus C, and where does it put the result? How many arguments do you usually have for an add instruction? Well, you need what? The 2 numbers to add, and what else do you need? Where to put the result. So why is there only 2 here? Someone raise their hand? Yes.
The answer goes in the second parameter.
Yes, the answer always goes in our syntax in the second parameter. So this is add EAX to EBP minus C and store the result into EBP minus C. So this is doing this A is equal to A plus B. And then what's going to happen right after this? What was that? Not yet to the epilogue. We have one more thing to do in the C code that we haven't done yet. Yeah.
Set the return value.
How do we do that?
Put 0 and EAX.
What's the exact assembly instruction?
Move 0, comma EAX.
Yes, move 0 into EAX, then we can have the function epilogue, which will be a leave and then a return, and then we should be good, and this function should be fine. So we can actually step through this very quickly so you can see how this plays out. I think we can do this pretty fast. So there's some value in this, there's some value into the stack pointer, some value in here for the base pointer. We set the current base pointer equal to where the stack pointer is. We then are subtracting the stack down by 10 hex. So now the base pointer still points at hex, what is it, hex 1000, 10,000, and then the stack pointer is going to point down. So we're going to move 10 into EDP minus C, hex 64 into EDP minus 8, moving that value into EAX and then into EDP minus 4. Finally, we move EDP minus 8, which is going to be 64, so we'll move that into, into EAX. Then finally, we will add this to whatever's in EDP minus C, which is A. So that should be 6E, which should be 110, and then other stuff's going to happen. So questions on this part?
Yeah.
Yes.
Why was the ESP moved downwards by 4 bytes instead of 3 bytes?
Yes. I think Yegana is working on ICTF, so she's not here. But if you see the email she sent out on the mailing list, that talks about why the offsets will be. It's probably because it wanted to be on a like 16 byte or whatever this is byte boundary. So on some systems that can be faster or something like that. Basically, the compiler makes a lot of optimizations like that. There are settings you can specify when you compile your application that says it's fine, go kind of as short as you can. Yeah, it's really interesting. I mean, this is why it's always really interesting to look at the actual binaries that your compiler produces because they can do kind of whatever they want. Any other questions? Yes?
Professor, can you go to previous slide, please?
Not easily. How previous?
Where we have the C code.
Look, maybe. Well, this tough part's actually kind of nice. I can scroll those slides. No, too far. Here?
Here we are not using C anywhere. So doesn't the compiler smart enough to know that it's gonna calculate only A and B and then use only 2 register to store A and B and then compile it and give it back to the program? Why does it even care for C?
But why does it even care, by that logic, why does it even care about A?
Because it's gonna print A, in fact it's not even gonna print it. So why does it even care for all these registers?
Because the compiler is really stupid, and I didn't compile this with any optimizations. And I mean stupid not in the not in a derogatory sense, but just in the when you compile it normally, you're not doing any kind of optimizations, right? And so everything just straight compiles one-to-one. And so you want your compiler to try. The worst bugs to ever debug are bugs that are in the compiler and not in your code. And the worst thing to ever know is to think that there's a bug in the compiler because there almost never is. It's always in your code. So you think the compiler's broken, but it never is, except for that one time out of 1,000 that it actually is, and then you go crazy. So by default, compilers, when they compile things, do it in a very stupid way, but in a way that they know is correct. Right? So just line by line compile it. So as you crank up the optimization level, then they will try to do things like dead code removal, and they'll do use analysis to see that nobody uses A to try to remove it. But even doing that is tricky, because who's to say that I haven't memory mapped this region where A is to some other process and we're sharing that memory region? Or what if, like in general, you can have memory mapped I/O, so you can talk to I/O devices through memory locations. So there, I would always want, whenever I specify assigned to that variable, that memory to be updated. You can add the volatile keyword before any, I believe before any variable type, and that will make sure that it always pushes that value back to memory. But so there, it's kind of a complex interplay there.
Yeah, just a follow-up on that.
Yes.
As per my understanding, if we compile this code, compiler is gonna check it for semantics, and then it's gonna recompile the code so that the instructions which are similar, they can tag it together. Is this understanding correct?
Not always. It depends. They can. So the compiler needs to make sure that the generated code still matches the semantics of your program, right? So at a high level, if the compiler is super smart, it can just compile this down to something that just returns 0. right? There's nothing, this actually does nothing externally. And it could switch, so if it decided that setting B equal to 100 was faster than setting A equal to 10, or that order was switched, it could do that, right? But it could never lift this A is equal to A plus B above the A equals 10 and B equals 100. So yeah, there's all kinds of, if you want to get into this, program analysis and static analysis techniques are all about dealing with these kind of issues. And that's the stuff I use to find vulnerabilities in research. All right. Function frames. Okay. So, we talked about the calling convention. So we need to know, when we call a function, we need to know, how do we get the return value of that function back? How do we pass the parameters to that function? How do we make sure that that function doesn't clobber our frame pointer, right? Because our frame pointer points to somewhere very special on the stack for us. And where should that function go when it stops executing, right? When that function's done, how does it actually know to come back to the program that called it, right? And this is very key, right? Because a function can be called by essentially any other function, right? You can't hard code where it's going to return to, and so we need that information stored on the stack as part of the function frame. Also local variables, and some temporary variables sometimes. So, we need a convention. So this is where somebody makes a standard that says this is the calling convention for this, this thing. And it's actually incredibly annoying because it varies by processor, OS, compiler, or the type of the call. So as we talked about, cdecl is the x86 on Linux calling convention. On Windows, same architecture, x86, completely different default calling conventions. Calling into system call, so calling into the Linux kernel through a system call from userland to the kernel is a different calling convention. It's the syscall calling convention. And so actually, you can actually write a binary that does multiple of these calls as long as you know which functions to call using which calling convention. So there's a way you can tell the compiler, hey, this function uses this type of calling convention. So it's pretty cool. But the Linux x86 calling convention, this is also something you need to commit to memory, which is just what we talked about. So the caller first pushes the arguments onto the stack from right to left. Right? So going from the top of the stack to the bottom is going to be right to left, and going bottom up is left to right on parameters. Then pushes the address of the instruction after the call, as we talked about with the call instruction. So that's all the caller has to do. So actually this is a pretty nice calling convention. If you want to call a function, all you have to do is these two things. The callee has to store your previous frame pointer onto the stack. It has to create space for local variables, and it must ensure that the stack is consistent when it returns. This is one of the most difficult and painful errors to ever debug. Because everything gets really weird. I was doing some this was in .NET, is it the CLR? What's the .NET? Is that like the assembly language or like their equivalent of binary? It's like the .NET. I don't remember, but we were rewriting .NET binaries essentially, and then you'd make some mistake where the stack is messed up, and it would just be like, this is not a valid program. Like, okay, that's an incredibly unhelpful error. You need to stare at code to figure out what's wrong. The other important thing is the return value is put in the EAX register. So when you call a function, should you have something important in the EAX register? No, because it's going to be clobbered by that function. There's actually also, as part of this, there's part of the calling convention is which registers can the callee clobber and use, and which registers does it have to save, like EBP, before it uses it. That's not super specific to what we're going through, so we don't have to worry about that too much. Okay, so let's look at an example of this. We have a main function, int I, a equals callee 1040. The callee has two integer parameters, a and b, return a plus b plus 1. Super simple. So just to reiterate what I said on Monday, if I didn't make it into a recording. This is something that you should be able to compile this by hand from the C code to x86. And it would look something like this. So what's it going to be? What's the first thing that main has to do? What's that?
Push EBP.
Push EBP. It has to save whoever called it EBP. Next, what does that do? Yes, move ESP into EBP. So we're going to set up its base pointer. What's the next thing it's going to do? Create some space on the stack. What's the minimum value it must have to create space on the stack? Has to be at least 4 bytes. It can be more, like in this case, when it's whatever hex 18 is. What was that? 16? 832. So it can do more, but it has to do at least 4, right? Because it has to create the space for this local variable A. The next thing that we're going to do is we're going to move hex 28 into ESP plus 4, so it's ESP plus 4. We don't know where the stack is, but it will be 4. What does that correspond to in the program? What was it? 40. Why? Why is it doing this instruction?
It's preparing some arguments.
Creating the local variables and the arguments.
Yes, the arguments to the function, right? They're not local variables, right? We're about to call this function callee, and we need the first variable that has to be on the stack is 40. The next one right below that, 4 bytes below that, has to be 10, right? So if we're going bottom up, right there has to be 10, and above that has to be 40. Now we've pushed all the arguments to the function on the stack in right to left order. And now we're going to call this function, which is going to push something on the stack. Now what do we do with the result? What's the next instruction going to be? Move what into where? Move EAX into where?
EAX.
Positive offset 8 of ESP.
Sorry. Okay, so we're going to move EAX. So we need to finish this A equals callee. So remember, we're a stupid compiler. We don't look at anything of the rest of the program. So we're going to move EAX where? Yeah.
EAX. Again, is it returning it?
Not yet. We need to do something with EAX. Where are we putting EAX? What was that? ESP minus 4?
EBP minus 4.
EBP minus 4, yes. So we need to get to the base pointer. We need to subtract. So we're a local variable A. We subtract 4. We're going to move EAX into that local variable, right? This is very important. This whole, you can think of this C line, this line of code, this line of main corresponds to these 4 lines of assembly, right? Because we first have to set up the arguments, we have to call the function, and then we have to store the return value into A. So now what we have to do? We have to do the final line of main.
Now we have to move the same value to EAX.
Exactly. So now we need to move EBP minus 4 into EAX. Now what do we do to clean up? Leave and return. Oh, done. So there's the prologue and the epilogue here. Now in callee, what do?
Push EBP.
Push EBP, so we're going to save EBP. Then what do? Move ESP into EBP. Next, what do?
Yeah.
What's different about this than the main example? There's no local variables.
We just have arguments.
Yeah, so we can actually just not, the compiler can actually decide not to move the stack at all because there exists no local variables. So then we need to move EBP plus C into EAX. What exact parameter is this? Who says A? Who says B? Like 4 of you raise your hands. How would you know?
Arguments are also stored from right to left.
So EBP is right where the stack currently is. What is EBP currently pointing to? What is stored on the stack where EBP is currently pointing? What was that?
The save base pointer.
Saved base pointer. So the very first thing we did in this function was push EBP. So that's the base pointer. What's directly above that?
Leftmost argument.
The saved EIP, right? So right above the saved base pointer is the saved EIP, which got pushed on there from the call instruction. And then what's directly above that? Which argument? A, and then B. So at EBP plus 0 is saved EBP. At EBP plus 4 is what? Saved EIP. Does that vary between functions? No. This is how we said the stack always is in CDECL functions, right? This EBP and saved EBP and saved EIP are always in this order. So the current base pointer points to the location of the saved base pointer. 4 above that is saved EIP, and then 8 above the base pointer is what? The first argument. So what's C above the base pointer? B. So it's going to move B, which in this case is 40, into EAX. Then it's going to move A into EDX. It's going to load the effective address into EAX. What does this do? What were the exact semantics of the load effective address? What was that?
EDX plus EAX into 1.
EDX plus EAX times 1. Yes, exactly. Into EAX, right? So a question you should ask yourself is, why didn't it just use an add instruction? Why didn't it do add EDX EAX? Because it just decided to. Yeah, I have no idea why. But the compiler does this frequently for doing additions. It does this load effective address, and mentally, it kind of always trips me up because I think of, oh, an address, it must be dereferencing memory or something like that. No, it's just simple addition. The load effective address specifically means don't dereference any memory, just do addition. All it does is EDX plus EAX times 1 into EAX. Now what do we do? So the question is, are we done with all the functionality of this colleague?
No.
Why not? What do we need?
Yeah.
We need to add 1, so we need to add 1 to EAX. Then what? Are we done with the functionality?
Yes.
Yes. We should be done. So now what do we do?
At lot.
Yeah, what is it? It's right there, so yeah. Except it's not. So why did it not do leave and return? What does leave do? Yeah.
Is it because it didn't use the stack?
Yeah, so what does leave do?
Puts the base pointer in the stack pointer?
It puts the other way around. It puts the stack, yeah, you're right. It puts the base pointer into the stack pointer, so it moves the stack up where the base pointer is. And then what does it do? Pop what?
The EBP.
Pop EBP. So it takes that value and puts it into EBP. So it takes save EBP, puts it into EBP. So again, the compiler decided, hey, I actually don't know. It'd be interesting to look how many bytes the leave instruction is. I bet it's at least 2. Because a pop is 1 instruction. I definitely know 1 byte. So I definitely know that. So it's saving a byte because the compiler knows, hey, I didn't subtract anything for local variables, so I didn't do any pushes in this function. So I know the stack is exactly the same as the base pointer, so I can skip that part of leave, and I can just output pop EBP and then return. Okay, once again, we have a prologue and epilogue. We just have a different prologue. Or epilogue. Okay, so. Now, the important thing is, when this is compiled, right, we can see in the program, and you should have seen this when you're looking at the object dump of part 3 of assignment 2, and based on the ELF header information tells the OS where exactly to load these code segments in memory, right? So that every time this program runs, these addresses, this code is at this fixed memory location. And this is why what will happen is the linker will say, oh, you want to call the function callee? Great. That's at memory address 804.83.94. Perfect. So that's why we can put a fixed address in here. And now the function foo name basically evaporates, right? It really doesn't matter at all in this context. If you notice maybe on part 3, there was only like 2 function names in that program. And that's because you can use this strip function to strip out all of these symbols from a binary. But I didn't want it to be too hard, so I kept some of them in there. Like the check password is a little bit nice, right? Because it kind of focuses you where to look. But I could have got rid of all of them, and then you just see like the entry point, and you have no names to talk about anything. It's also cool to get rid of all of the debugging symbols and everything else, so you don't have any variable names that you can kind of look at. Yeah.
So you mentioned about temporary variables, right? So in
Yes.
case we have a temporary variable, where does it go into the stack?
It depends. I think that it would depend on the compiler. The compiler could decide to just make it a local variable, so to create kind of a fake local variable and add it to the local variable, so it just allocates more space for the local variable, and then when it needs it, it copies it into there. It could also, for that part of the assembly that it uses that, it could push something onto the stack and then later pop it off into a register. So it really depends on the compiler and how it decides to do things. But both ways use the stack. All right. So main is just at some location here. And so, so the only thing we need to know to start executing and simulating this function is what? What address in memory do we need to know? We know main, okay, at 804.83.85. So if we start executing main, then what's going to be in EIP? Which is 804.83.85. What else do we need to know? We need to know where the stack currently is, right? Because we're going to be moving the stack. So let's say it's at FD2, D4. This was actually something I observed on a real system. Yes. And so we know this, so we know because of that, the value inside ESB, the stack pointer, will be FD2D4, and we know that the next instruction that's going to be executed is going to be main because there'll be the value 804.83.85. One of the things you'll note, yeah.
So looking at the diagram, are we assuming this program that's running this code has exactly 4 gigabytes of RAM? Like because it has the memory address all the way from FFFFF to the all zeros.
So this is a 32-bit process, right? We know that because we know it's an x86 program. And we know that a 32-bit application could potentially access 4 gigs of memory.
Yes, and also since all the instructions are stored at the fixed memory address,
Yes.
what if it's running on a computer that has a tiny memory that doesn't have those memory address?
So the operating system takes care of all that for us. So that's why we love operating systems, is because they let the process think it has 4 gigs of memory.
Oh.
And the operating system deals with this fact of, hey, I actually only have a gig of memory, or I only have 512 megs. And so what the operating system will do is that's what it uses the swap file for. So it will try to keep the most recently used and the most frequently used bits of pages of memory in actual memory, But if some other process needs more memory, it will swap out a infrequently used page to disk. And then it will try and bring that back in. So yeah, that's the operating system deals with all of this using the virtual memory management system. Cool. Okay, so what do we know about what's currently in EVP? Or what's a valid assumption we can make about the value inside EVP? Yeah, it's the previous function's base pointer, so what does that tell us about the value?
Greater than or equal to ESP?
It should be greater than or equal. It needs to be somewhere above us, right? Because if it was below us, it'd be garbage and we could overwrite it. So we know it must be something above us. I'm not actually, no, I think this is wrong, right? Yeah, that's fine. Pretend it's above us. That's something you're supposed to catch. So then when we first execute this, we're going to push EVP. And so we didn't draw it, but what's right at that memory address FD2D4? What is at inside that memory location there? If we tried to dereference that, what would that tell us? What is that?
Instruction.
It's an instruction on the stack.
Oh.
Address of the main function?
Address of the main function? No. Yeah.
The end of the stack of whoever called me.
What do you mean the end of the stack?
So isn't there a function that called me?
There is.
And then
So what's on the stack right there?
EVP. Right?
No. So close.
Next to picture.
Yeah. Wait just a second.
Save.
What was that?
That is the stack. That value is the stack.
No. I think so. Said over here.
Extension can be read after the calling function.
Yes. Not after callee. Because main, right? Some function called main. So it had to do call 80483A5, and as part of that, it pushes the next instruction to go to after that to execute, right? So this actually makes sense if you think about it. When you return a value from your main function, what actually happens with that value?
It is passed to some other process.
It's what?
It's passed to some other process.
It's returned where? Where can you get?
It's the exit code of the.
It's the exit code of the process. Does main set an exit code of the process? No, it's just returning a value from its function. So there's actually another wrapper program that runs main. It calls main, it gets whatever this return value is, and it calls, I think, probably system.exit with that return value. And that becomes the exit code of your program. Sorry, people are hanging on Slack. Oh, I can't actually. I can turn it off here though. Mute it. Okay, so we know that right at memory address FD2D4 is the return address, the saved EIP of whoever called main. Right? What's right above that? argc, yes, the first argument to main. And what's above that? argv. And what's above that?
Environment.
envp. Yeah, we'll see that next. That's actually also passed in the main. Great. But now when we think about main, what main does is it pushes EVP, which moves the stack down, and copies whatever was in EVP onto the stack. Right? So now we've saved the previous function's base pointer. Now we have to move the current stack pointer into the base pointer. So now the base pointer points to where we are and not somewhere way above us on the stack. We subtract hex 18 from ESP. We then move hex 28 onto ESP plus 4. And then we move 10 into where ESP is. And then we call 804, 83, 94. So when we call what is the value exactly that's going to be pushed onto the stack? 804.83bf, because that is the next instruction we want to execute when this function returns. So when we call this, remember call is basically push the next instruction and set the EIP to whatever this value is. So it'll move down and it will copy 804.83bf into the stack, and the instruction pointer will get changed to the first instruction of call E. Then this will execute, right? Call E just got called, right? And this is why we can know that main is no different than any other function, right? So this is the same circumstance that happened right when main got called. We said, what exactly is the stack pointer pointing to? It's the same EIP of whoever called it. And we have to push our E. We have to now set up a new stack frame, so we push EBP. So now we save main's EBP onto the stack. Then we set the current stack, the base pointer to the current stack pointer. So we move the stack pointer to the base pointer. So now we've set up call E's base pointer. And now we're good to rock and roll. So now we can move EBP plus C, which gets the parameter that's passed into this function. And we know it's 1, 2, so it's going to be 4, 8, 12 up the stack. So it's going to be 28. So it's going to move 28 into EAX. And we can see that if we kind of think about the stack frames, right? We have main has its function frame, and then we have call E has its function frame. And it's a little bit weird because there's a little bit of overlap there with the arguments, but you know, that's kind of fine. So we can continue. We can move 28 into EAX, we can move A into EBX. We can add them together, put the result in EAX. We can add 1 to EAX. Then we can pop EDP. So now we're all done. We're going to pop EDP. We're going to put FD2D0 back in the base pointer, which is going to restore main's base pointer, right? Which should put the base pointer back up here. And now we're almost good to go. So now, what does the return instruction do? What was that? Yes. So takes pop, it's essentially a pop EIP. So dereference the stack pointer. Wherever the stack pointer currently is pointing to, take that value and copy it into EIP. So that's the next instruction that we're going to execute. So we do that. We're going to go down here. And now we're going to move EAX, which is hex 33, into EDP minus 4, which is going to be the local variable A. Then we're going to move that back into EAX, which we know doesn't change things. Then when we leave, what's the result of the leave function going to do? Where's it going to put the stack? So you have all the memory addresses. Which memory address is ESP going to be at after this is done? Yes. FD 2D0, 2D4, right? Remember, the leave does two things. It sets the base pointer to the current stack pointer, so that's the first part of what it does, but it's not done yet. It still has the second part. The second part is pop EBP. So then take the value that we're currently pointed at, pop it, which moves the stack up 4 more bytes, and it copies that value into into EBP, and now we're done with that. So it's very tricky, but very precise of what it does, right? Puts it there, pops it up. Here we go. Then we leave, or then we return. So now we're going to start going and executing at whatever address is up here at memory address FD2B4. So, key thing to think about. How did Kali know to start executing this instruction?
Got saved on the stack.
Save EIP.
Yeah, if we rewind this program, which actually, if you've never used a debugger, used a language that you can go backwards in, it's actually really cool. If you ever do any like OCaml programming, they have a debugger where you can actually move backwards through the program's execution. It makes tracking down bugs really cool. Okay. So this is actually going to be the critical thing when it comes to buffer overflows, right? The only way that this callee function knows to go back and start executing this 80483df is the fact that there is the memory address 80483df on the stack here. If there was any other value in here, what would this return instruction do? Go and start trying to execute from that value. What if it's 80483A5? Main will start again, and it will do exactly what it does, right? It doesn't know that it was called from the return of callee. It just, these instructions just start executing. It pushes EVP, it moves the stack pointer to EVP, it subtracts that, it does all this. So let's think about this. Oh yes, question.
Why does main subtract 18 hex from ESP when it doesn't need that?
Because?
Compiler.
Yes. Yes.
So if you were trying to jump to a function that had arguments, you'd have to also, in your buffer overflow, write to the registers, or not registers, the addresses above that. So when you jump to it, it goes.
We will get there, yes. But key thing to think about here, right, when we think about, we looked at ELF headers, and we looked at the different sections of memory, right? And there were different permissions on each section of memory. So, is the stack writable? And how can you prove that to me?
The permissions in elf header?
No. I mean, not know that you can't, no I don't want to. I want you to prove it to me.
Every function needs to write to it.
Yeah, look at this. We're pushing things onto the stack. When you push something onto the stack, what are you doing with the value that was previously there? You're overriding it. Literally, to call any function or to do push EVP, we have to write to the stack. Right? Fundamentally, for the stack to even be useful, it must be writable. It also must be readable. Right? We got to be able to read stuff off the stack that we write there. Otherwise, it's also useless. So, what's to stop callee from either accidentally or on purpose writing to this value here? Should it? Should a well-written program ever write to that? No. Right? Because a well-written program will only write to the memory addresses that was specifically allocated to it, right? And there's nothing in the C code that corresponds to that memory address. It just happens to be, because of the calling convention, that the variables are mixed in on the stack with these return addresses. What if I also, before we get here, before this pop EDP, what if I alter the value that's at FD2B0? What would that do? Change main's base pointer when we return. So now main thinks its function could be somewhere completely different. Right? That's actually another type of attack that we'll end up looking at. So these are really key things to understand about buffer overflow vulnerabilities. Fundamentally, and I think of these saved EIPs like, actually asked this in another class, but this is similar to, if you've never heard of it, the story of Hansel and Gretel, which is like this fairy tale where these two kids go off into some scary woods and they have this really smart idea to not get lost. They'll take like a loaf of bread and they'll put breadcrumbs on the ground every few feet. Right? And so that way when they want to get home, how do they get home? They just follow the breadcrumbs home. Right? This is exactly like this. You can have a function, call a function, call a function, call a function, call a function on the stack. Right? And all of those saved EIPs are your breadcrumbs of how to get home. So what happens if you're in the woods and some birds eat your breadcrumbs? you're lost. And what if an evil witch takes your breadcrumbs and instead of going back to your house, changes the breadcrumbs back to her house? Where are you going to follow and go? Her house. That's exactly buffer overflow. So the idea is you want to change and overflow this return instruction pointer to go to your code and not the program's code of where it was originally intended to go. And being able to do it precisely and reliably requires really understanding at a fundamental level what's going on here. Not only the x86 code, but also the memory and the stack. Okay. All right. So, a stack overflow or a buffer overflow is really any time that an attacker that we can try and write to the stack and try to overwrite this either save VIP or the save base pointer. We're going to focus mostly on save VIP, but the principles usually apply to save base pointers as well. So, when you declare, I'm tired of the slides, let's go back here. Not there. So you have some C code. You guys like doing make? We'll do another one. How much space does the compiler have to allocate for this function foo?
More than 1,000 bytes.
How much? 1,000?
More than 1,000 bytes.
Not very specific. Yes.
Just the variables, 1,004 bytes.
1,004 bytes just for the variables, right? The local variables has to be at least 1,000 bytes for var and another 4 bytes for x, right? So this is, your stack can actually grow pretty big because you have people declare buffers like this. So what's the alternative to doing this? So what do I need to have on the stack? Now how much memory is allocated on the stack? 8 bytes. 4 bytes for the character pointer. Remember, pointers are 4 bytes because they have to refer to any memory address, even though it's only pointing to 1 byte because it's a character. And int is 4 bytes, but here we're allocating on where? The heap, 100 bytes. So now what happens, so let's get rid of this x. And let's say the compiler gave us exactly 100 bytes for our local variables. So let's say I did what did I do? So it depends on exactly how the compiler lays out this program, right? So that's another important thing I want you to understand, is that really the C code is just your guide. You should always look at the assembly code to understand exactly how to do it. You can get by kind of looking at the C code and doing stuff, but really you can be much more effective. You can be a lot faster when you're solving these challenges and problems by looking at the assembly code. And actually it's it's a skill that like security professionals love. So if we think that this program has 100 bytes on the stack, so this would be the address of var, right? That has, not x, it has 100 bytes on the stack. So we set up EVP, so EVP EBP is here, and we subtract 100 from ESP for the local variables. So what's at ESP plus 100? Right, save EBP, and what's 4 bytes above that?
Save
Ooh, so this is wrong, right? So where is this going to address? Will this type check? What type is this? Character. What type is this? Character. What's this type? An address. Can an address and a character be the same type? Oh, we have a problem. We either need to cast something here. So specifically, we're looking at 100 bytes. What's the 101st byte plus ESP, or plus bar, which is where the ESP is? It is 1 byte inside EBP, so it would be this byte here, right? So to get to EIP, which would be above that, I'd have to go 1, 2, 3, 4, and then I can only control it a byte at a time. So it's that example with the character array. But the idea is I can access, right? There's nothing, as we saw in C, there's nothing that prevents me from accessing outside the bounds of an array. And if I know exactly where that array points to on the stack in relation to EBP and the save VIP, then I can know exactly how much I should overflow to get to that save VIP. And so if we're just writing random gibberish, right? Let's say we have a buffer of 100 bytes, and we give it 1,000 A's, so it does a string copy. So it does a string copy from our input to the buffer on the stack. And string copy is just as stupid as every other function. It's going to take a byte, copy it over, increment the pointers, say, is this the null byte? Nope. Copy it, increment, keep going. And it'll copy 1,000 bytes over. And so what happens then to the save EIP and the save EVP on our stack? Completely overwritten, right? And so then what happens when that return statement executes? Where is it going to try to return to? Yeah, it depends on if we use uppercase or lowercase a's. If we use, I don't remember which is which. I think lowercase is what, 61? 62? Lowercase a? Hex, in hex.
Pretty sure it's 62.
Decimal, who thinks about decimal ASCII characters? I think it's 62 in hex. So it would try to access, it would try to start executing from memory address hex 62, 62, 62, 62, which is probably not allocated to the program, so it'll get a segmentation fault, and it'll crash. So normally this can cause a segmentation fault. But if we craft our input correctly, and we put the bytes in exactly the right order, we can control what value is copied into that saved EIP, and therefore we can force this program to execute any address of our choosing as its next instruction that it goes to when it returns from that function. And so, as we'll see, so this is a little bit of a hint going forward. We're kind of exploring this in a historical perspective. So it used to be that the stack was executable. So the program would actually jump to and would execute anything on the stack. So as long as you can put some code that you want to have executed into the process, and if you change that EIP to be at the start of that code, now the program will start executing your code on the stack. Yes?
Do people actually use that non-maliciously in their code?
Yes, so this is exactly how JIT works. So when a process is JITting, right, it takes like, You can say JavaScript code, and it looks at it, it sees how it's executing, and it compiles it on the fly to x86 code. So it really takes and generates x86 code and has to jump and start executing that x86 code. And it's usually on the stack, or they have to deal with memory regions and making them executable. So yes, so there's been measures taken since there, but we will kind of go and take this historical perspective of, okay, this is how exploiting buffer overflow was done, and so we'll see what prevention techniques were made from that, and then we'll see ways that clever, crafty attackers have got around that. So hopefully by the end you'll have zero faith in any defensive measure, because attackers are very smart. And so we'll get into exactly, we'll call this just shellcode right now without thinking about it too much. We'll look at exactly how to write shellcode, because code has very certain properties that we need. This code that we want to start executing from could be part of our buffer, right? So if the original buffer is 100 bytes, we know we basically have 100 bytes at least up until the saved EIP. And so if we can make our shellcode fit in those 100 bytes, we can actually put that there and try to jump back to that shellcode. We also may be able to put it somewhere else. We may be able to put it somewhere else in memory, as long as it's somewhere in what kind of memory region? Executable. It has to be executable, right? For us to jump and start executing it. And the key thing that we've been talking about, this is why we studied Unix and Linux applications, is that the code that's executed will be executed with the privileges of the program. So if this is a setuid application, it will be executed with setuid privileges. So we can look at a super simple example of a function that, okay, good. Of a function that copies from a parameter that's passed in into a local buffer, and string copy doesn't know about any sizes. What are the parameter types to string copy? Character pointers, right? And see, character pointer has no metadata about how long this string is that, or how big the buffer is that this character pointer points to. Right? So there's nothing to stop string copy from copying over foo. And string copy itself is really fundamentally insecure. Because the semantics of string copy is copy bytes from string into foo until you've reached the null byte of string. Right? So if the left side is ever a fixed location, and the right side depends on unbounded user input, you can always have some sort of vulnerability from that. Because if you can't bound the input, then you're toast. So the main function, I took this from my old CSE 340 class as a hint, if you ever become a professor, never put dates or class names in your slides. This is impossible. So we can do this, then we can print after, we can return 0 just to see what happens. So if we compile this, we'll see that we do our normal epilogue, we push UDP, we move the stack pointer into the base pointer, we subtract 10 from the stack pointer, we move 804, 8504 onto ESP. What is this? It's what?
Address of that string.
Yeah, how would you go about verifying that? Object dump might help. What else? How would you figure out what section of memory this is? What was that? Well, hopefully it's read-only data, but how would you verify that assumption? Readelf. You use the readelf command to look at the elf segment file, the segments of this binary, and you'd see that hopefully 804, 8504 is inside the read-only memory region, because this is a constant fixed string. And that's exactly why the compiler can put a constant address here, because it knows that the OS will load that at a fixed location. And if you look inside the binary, you will see at the offset that the OS says 804, 8504 starts at in the binary. you will find the bytes that correspond to ASU space CSE space 340. Then we'll call this myCopy function. So now we've set everything up, right? We passed in our parameter. We've copied that value onto the stack. We call myCopy. We then move 804.8517 into EAX. What's this? Yeah, there should be the string AFTER0, right? There should be a null byte at the end of this. Then we'll move EAX onto ESP. That's weird. Huh, that's crazy. That's like exactly the same instruction, but it's this one's two instructions. It's using EAX, and this one's doing it one. I don't know why. Calls printf, and then moves 0 into EAX. Calls leave, and then return. So myCopy is really simple. It's going to subtract, 28 from ESP hex. Then it's going to move EDP plus 8. What's EDP plus 8? arg0, which in this case is the str, the string parameter, which will be 804.8517 when it executes. It will then move this value EAX into ESP plus 4, which is going to be the rightmost parameter to string copy. Then it's going to put what into EAX? Zero? What was that?
No return statement.
Can't hear.
No return statement. 0.
There's no return statement, but
So it's going to call photos for food.
yeah. So this is actually this is the important point of load effective address, right? It is not saying dereference whatever is at EDP minus C. So we know it's minus. So we know what about that? It's below EDP, so what do we know about that? It's a local variable, right? It is not saying move the value that's at EDP minus C into EAX. What's currently the value inside EDP minus C?
Probably the older one.
We don't know. It could be anything on the stack, right? All we did was move the stack pointer down hex 28. Whatever junk was there will still be there, right? We don't know what's there. And so now we need to, so remember the load effective address takes the value inside, the value in the EDP register, which points to the base pointer. So it takes the address of the base pointer and it subtracts C from it and it moves that value into EAX without dereferencing it. So this will be essentially the address of foo. So how many bytes exist between the buffer foo and, let's say, the current base pointer? C. So then how many bytes between foo and the save EIP? We have C, and then you gotta get 4 more bytes to get to the, so you have C, we got something to C. 12, we have 12 bytes, we have 4 more bytes to get past the base pointer, so that's 16, and then the next 4 bytes will overwrite whatever is in EIP. And we know that not from looking at the C code, because from the C code, we would think that it would be 4 bytes only, right? There's only one local variable, it's 4 bytes. But from looking at the assembly code, we know exactly how many bytes it is. So then we move EAX into ESP, and then we call string copy. So what's string copy going to do? It's going to do exactly what its specification and its man page says that it's going to do. It's going to dereference the byte of string, and it's going to copy it to dereferencing foo. It will increment both by 1. It will copy a byte, increment both by 1 until string points to a null character. That's all it does. So stupid. then it leaves and returns, because there's no return value here and stuff. So, if we look at this and step through this quickly, we will see, we'll push EVP, we'll move that, we'll subtract the stack down, we'll move that onto there. We'll see we actually need a much bigger stack than we previously had. We will then move, so the important part here is right before the string copy, right? So the arguments of string copy, the first one, so the first argument is FD2AC, which is this address on the stack. Above that, the second parameter is 804, 8504, which is the string that we passed in, that constant string. So when we call string copy, what it's going to do is copy that ASU space onto, so A will go at FD2AC, S will go at FD2AD, and so on and so forth, those 4 bytes. The next 4 bytes will be copied above that, 4 bytes 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 above that. And so now this returns, now when we get to the leave and return, the leave puts everything here, now we return, what address is it going to try and execute from? Where's it going to start trying to execute? Oh, I guess we weren't done with the leave. Oh, yeah. So the leave instruction, so ret is going to do what? Pop EIP. So it's going to try to start executing from 31303220. So it will probably cause a seg fault. And when I ran this program, when you run it, you will get a seg fault. And you can do this too at home on your own computer. You would definitely get a seg fault, I think, depending on how much space is on your stack. But, you know. And the very cool thing is if you run this in GDB, and you run it, it will say, hey, I'm starting this program, and it'll go, I got a seg fault. I got a seg fault. I tried to access memory 31303220. Which means you know exactly where that happened. So you can do fun things like change this program, and these 4 bytes, let's see, is this 1, 2, 3, 4, was that fault? No, it's a space in there. This one? Anyways, you can change these bytes, and you can change them to whatever address you want. So you can make it loop back to itself, you can make it do all kinds of cool stuff. And if you look at the registers, so on GDB, you can do info registers, you'll see exactly these values in there. You'll see that EIP has this value. And fundamentally, once we can control EIP, we can make the program do whatever we want. And that is ultimately our goal with all of these binary exploitations, is we want to control EIP. So, remember all this, because we're going to get back to it over the break.